I'll be briefly presenting on some of the work that we've been doing as part of the system integration subgroup that Johannes heads and Amer and several others are also part of, right? And I'm joined by Hatem from my group. So what we have done is try to sort of identify several quantum classical workflow patterns, right? So some of these are application patterns, some of these are more operational patterns, right? And the idea is that you want to sort of try and find structures that or patterns that are very repeated and try to synthesize those, because those might be your building blocks for subsequent like decisions on sort of scheduling, placements, and so on, right? And through this, we are initially trying to capture the data and control flow of such hybrid quantum classical applications, and also eventually try to identify what kinds of the quanta of data that flows between them, the amount of computational intensity, both from the quantum as well as the classical side of things, and various dependencies that lie between them. So there's an initial effort in the last couple of weeks that we thought we'd present and get feedback from the rest of the community. And besides the patterns, we're also looking at how the integration of these happen, right? So how are these patterns and is going to be mapped onto the underlying hardware infrastructure, and what are the decisions that come into play at that point in time, right? This gets into what's the available compute capacity, what are the queuing and scheduling policies, what are the latencies, bandwidths, and so on for the network interconnect, both in local as well as wide area, and so on, right? So these will come downstream based on the motivations from these workflow patterns, right? One thing we also try to initially do is try to initially identify the deployment models. Again, by no means are these exhaustive, but these are some things that we felt that would be useful at first glance to take a stab at, right? So one is sort of the on-prem, where your quantum hardware is co-located with your classical, and typically this would be in a HPC center that you would have that. And here you could have quantum lying on the same rack. I think we had some presentations on these in earlier meetings, where they have very tight coupling between the quantum hardware and the classical hardware, right, within the same rack. Or you could have it in the same data center, but on neighboring rack, right, where the network connection is still within the local network, but it's not, the latencies might be slightly higher, or the bandwidth might be slightly lower. They're not necessarily near real time at this point in time, but they are within the same data center. And then you have the off-prem or the far quantum variants, right? So where the quantum sort of hardware or quantum HPC center is in one location, but it's also used by other HPC centers which might be purely classical in nature through various APIs or through tunneling and so on, right? So that's another variant that we sort of recognized. And yet another variation of this further down is when you bring in cloud itself as a first-class infrastructure, which complements your quantum HPC and your HPC centers, which typically could be used for quick dry runs or sort of small-scale testing and so on, just as part of a development lifecycle. And then maybe you start using your bigger sort of hardware, right? Or you could sort of complement your available quantum hardware with cloud-based credits and so on as well, right? There's another far quantum variant that we sort of recognize, right? So I'm sure there are more permutations and combinations, but we thought this is a good starting point to identify and then sort of see how some of these applications that we'll be talking about can eventually map onto such deployment models. So switching into the workflow patterns. So these are things that we identified from various literature. Some of the work that we'll talk about has been done in our own group. And we still have, there's still a work in progress. And then we're still sort of having weekly sort of meetings to identify newer applications and so on. So I'll briefly talk about that towards the end. So one of these is a classical variational quantum sort of kind of model, where you have, and all the blue ones are the classical bits, and the pink or sort of orange ones are the quantum tasks, right? So here you essentially have a sort of more tighter coupling between your QPU running sort of fixed circuits with different parameters, and a classical optimizer sort of consuming the output of that and tweaking sort of the initial parameters and rerunning this circuit. So here you see a more tighter coupling between the classical and the quantum in a closed loop, right? until they sort of converge and until they reach an optimal set of solutions. So this is sort of your classical variational circuits that have been commonly used, right? So here the key thing is that there is a tighter coupling between the quantum and the classical parts. Another one is in terms of SQDs. This is quantum diagonalization techniques. These are an emerging class of sort of applications. I think IBM is gung-ho about that. There have been various demonstrations both with RIKEN as well as ORNL in the context of primarily quantum chemistry. And here the idea is that the quantum sort of task serves as a sort of initialization, right, for subsequent sort of HPC jobs, right? So the quantum sampling essentially tries to reduce the sort of space within which you have to sort of find various solutions, and this ends up sort of going from a potentially exponential space to a much more manageable space. But there's a one-time, typically it's a one-time task that happens, and subsequently this spawns off multiple parallel HPC jobs, right, which tend to be much more computationally intensive, right? And this is one clear case where you have the need for HPC requirements, because many of the other examples we've seen so far, the HPC requirement is not strongly motivated, but this seems to be one of those emerging class of applications where that's much more clearer. In fact, the classical task is probably going to be more time dominant compared to the quantum sampling task, right? And there's an optional feedback loop where you can go and improve the sampling based on sort of observations with initial parameters and biases, and then sort of rerun the whole cycle. But typically, quantum is a one-shot affair, after which it's purely HPC in nature. And here again, there's not so much tight coupling, it's more of a pre-processing, after which the classical takes over. Another one is in the context of quantum sort of support vector machines and quantum machine learning. And here the idea is that you encode your sort of both your data labels and features, as well as your sort of SVM kernels as circuits, and these are sort of parameterized, and you're also able to shard the data, right? So in a sense, you can sort of do a data parallel execution by encoding the data as different circuits. And what that gives you is a set of these kernel circuits and the data shards, which you can then run in a parallel manner for the training process, right? And this, again, this kind of a fan out can happen in parallel on potentially different quantum sort of hardware. So this is one example of being able to use multiple quantum computing sort of QPUs if you have access to that. And this is one scenario where you might potentially, even if a single data center might not have sufficient quantum capacity, you could potentially parallelize it onto multiple, even far quantum sort of hardware that's available, right? And this, once your sort of kernels execute, you then have a classical step where you merge the sort of kernel outputs back together to the trained model, and then again you can run a test circuit using your test data in a similar manner using the trained model. And this again has a similar kind of workflow that happens, and you sort of are done with this, right? So this is an example of, in a sense, data parallel execution of multiple circuits. But here again, there's no tight coupling as such, right? So because there's no sort of, this can happen in a more leisurely manner. The end-to-end time, of course, is going to be affected. There's no need for tight coupling between the quantum and the classical parts. Another sort of variant of this is the quantum neural network that has a similar kind of approach over here. So where you sort of run your parameterized circuits onto the QPU to get various expectation values, and then you sort of update these weights on your sort of on the classical side, and then sort of do that iteratively till you sort of converge. This is sort of similar to the QSVM kind of operation. So these are sort of two variants of the quantum machine learning sort of steps. Here again, there is no sort of tight coupling. Eventually, as long as they're able to execute and converge, that's good enough. So then we get into a set of workflows that are more partly not application driven, but more optimization driven, if you could say that. And then it's not necessarily the application exposing certain characteristics that they could be optimized, and based on that, you're actually starting to do modifications to the circuit in order to expose more deployment or scheduling options over here. So one of these is the dynamic circuit generation. Here, again, the idea is that you would start running a circuit, and you do it's running, you sort of do mid-circuit measurements, and then you sort of decide whether you want to sort of change the characteristics of the circuit, right? And in that case, you go ahead and sort of modify the sort of circuit, and then sort of and change the structure of the circuit, and you sort of keep doing that. So here again, there's a need for a much more closer loop between the quantum and classical, right? Here you can't afford to have a lot of delay between the quantum and classical, unlike some of the earlier applications. So here, a tight coupling between the quantum and classical is required, right? And the effect of the classical informs the behavior of the quantum, and vice versa. Another one is a sort of fairly common technique in terms of execution of larger circuits, where you can potentially split the large circuit into smaller sub-circuits, and then run these concurrently on different QPU hardware, right? So a couple of reasons that we've found this to be helpful is that you can sort of parallelize the circuit, so you can potentially run it in a faster manner. And we also find that sometimes it's easier to get to the top of the queue in a sort of lower qubit hardware compared to a higher qubit hardware. The competition is lesser. So if you look at the end-to-end make span, including the queuing time, sometimes it's faster to run on 2 or 4 or 8 smaller qubit machines rather than one large qubit machines. Of course, you're going to sacrifice a bit in the quality, so you'll have to run it more times. But depending on how the scheduler is working, you might actually end up completing it more quicker for a comparable set of accuracy, right? So here again, you are given a circuit. There is some optimizer that figures out how many sub-circuits you can potentially split it onto, and then potentially jointly with some scheduler sort of logic, you can decide what's the ideal number of sub-circuits you want to split it onto, and then you launch them onto different QPUs, and then you combine the result and you go forth with it, right? And how many sub-circuits you split it onto can be a dynamic runtime decision that you make depending on sort of real-time conditions. Okay, I think that got reordered. Oops. Give me a moment. I'm suddenly missing a couple of slides. That's strange. So anyway, so there are still a sort of few of these that we are sort of looking into. There's one more that we are looking into in terms of doing these QIC circuits, quality indicator circuits that we run, where you can sort of so you can run these trial circuits that are much smaller in size, since you are sort of since you don't get access to the noise information very frequently. So there's some work that we've done with IBM where you run these quality indicator circuits that are specific to user circuits but much smaller in size, for which you know the final end product in terms of how the output should be. And based on that, you actually decide what should be the ideal layout for a particular sort of end user circuit, right? So that's essentially like almost like a pre-processing circuit that you run of a smaller size, which then immediately informs the layout of a larger user circuit, right? So there again, at that point in time, you need somewhat closer temporal proximity between your QIC quality indicator circuit and your final circuit, because the larger the delay, the more the noise profile is going to change, right? That's one variant that's also there. And there's also another one where you have essentially various zero noise extrapolation or probabilistic error correction kind of circuits, where you take the original circuit, you sort of run different variations of that in parallel across different QPUs, and then you merge the outputs from all of them together, and then get the final output. So this, unlike circuit cutting, where you're intentionally splitting the circuit into different parts, Here you're running different permutations of the same circuit, potentially with different layouts, and then running them in parallel, and then combining results together. So here you don't reduce the size of the circuit as much as trying to try different variations of the circuit so that your time to convergence and the quality of your output increases, but by using a larger number of QPUs, right? And what we are also in the process of doing, and this is as part of our weekly conversations, we are also just late last week we had a discussion around MCMC circuits. That's again a very recent paper that came out last month. This again has the potential of requiring quantum plus large HPC. So this again might have some interesting consequences for quantum HPC, similar to the SQD problem. There's also a NERSC report that's identified 6 applications from materials, quantum chemistry, high energy physics, and so on. We're again having a series of talks from some of these groups so that we can start adding those workflows into this workflow patterns deck of slides as well, which by the way is maintained in our Confluence site, right? And some of the questions that we hope to additionally, we want to sort of add more details to some of these workflows. Right now we have the high-level patterns, but we'd also like to identify how tightly coupled these are, right? So how soon should the quantum and classical work? Do they have to work order of seconds or milliseconds within each other? Can they run into minutes or hours apart? Is that going to have an impact on the correctness or the quality, right? Obviously, the user wants to get it done as soon as possible, but the question is, modulo that, right? Is the correctness of the application itself affected by the tight or loose coupling between the quantum and the classical bits? Also, how much data flows between the quantum and classical parts. So this can affect, again, the type of deployment model, whether you can run it in a far or near quantum and so on. So that's, again, something that we're trying to identify as part of this effort. And also sort of the computational intensity. In fact, many of the applications we've seen, the classical part is not really stressed a lot, right? Which sort of, and that's really not good from a quantum HPC perspective. Again, the MCMC and SQD are 2 emerging examples where that's starting to change, besides the NERSC papers. But that's, again, something that we're trying to characterize as part of this effort. And all of these can help us with subsequent downstream, right? So what's the right deployment model? What's the right system sort of model? What's the kind of scheduling that we should think of, or co-scheduling we should think of? What are the parallelizations, so on? All these things can flow once a sort of thorough job of this characterization is completed, and we have like a reference set of these patterns that can then form building blocks for making these decisions, right? So that's pretty much what I had, and the hope is that there's a lot more conversation that happens that can drive some of the discussions that we are having as part of the other subgroup, right? So happy to take questions or comments. Yeah.
Go ahead, Masud.
Yeah, so I want to mention that thanks for this. It was a very nice presentation, but quite a few different categories that are still missing. One is in the hybrid quantum classical sampling, where basically the quantum and classical processors working together in configuration space. So basically they're exchanging bit strings on the runtime all the time. This is one of the examples of tight integration. You can think about, like, let's say, a hybrid with parallel tempering, where like you invoke quantum processors time to time, and you can think about QAOA or annealers, and you do reverse, annealing. You start with the classical good hot start. You give another hot start to classical processor. This could happen super fast on the time scale of, hundreds of spin updates per nanosecond. On FPGA, if you do it like on a probabilistic computer, this is one of the, I would say, extremely tight integration needed. The other one is the class of circuit kneading, adaptive circuit kneading, where you have mid-circuit measurement and feed-forward operation at the workload manager, where you need to actually distribute the jobs based on the previous measurement outcome, and you need to have quantum coherence present. That it's another tight integration. So this can be applied to any and all kind of the algorithms or workload patterns that you set, because it's kind of on top of it's just your workload manager. So you can run any application. It means that you need, for all the situations you consider remote access or like tight integration is not required, it would implies that you need tight integration even for those. There are certain things that you need to push the HPC to the limits, even to the front, like leadership machines. Let's say for phase estimation and other applications that you need to prepare very good high quality starts to minimize the cost of quantum processor, then the HPC kind of the compute could be very intensive. I think this is answering one of your kind of comments that you mentioned earlier. The other thing is that you can consider a combination of the dynamical circuit generation that you mentioned in the context of like a quantum recurrent neural network or quantum transformers, where you keep basically having stacking different layers of quantum neural networks, where each layer depends on the previous measurement and the previous layers, and those are another class of tight integration. So I can mention a few more, but let's just stop here. Thanks.
No, this is wonderful, Masood. It'll be great if you could sort of put out a few archive papers or links on the chat. I mean, this is exactly what we are looking for, the feedback from the community. So we can sort of go back, read those, and formalize some of those structures as part of this working document, right? It'll be great if you can add some of these links.
Yeah, we can sync offline. Yeah, there
Sure.
are some of these are papers are already on archive, some are in preparation. But do you have any preprint of your presentation today, or something that is are already?
This will be there on Confluence. We should be posting it right after this. We can send a link on Slack with access to that. You should be able to download that. Yeah. Or Amir will probably put this on the GitHub page as well, right? I'm guessing. Or do we want to keep that in Confluence for now? Yeah.
Yeah, and I can put the Confluence notes, like the links as well, so that everybody has access to it.
Yeah.
Yeah. So, but also, I think we should discuss like kind of situations that are, let's say QPU centric versus quantum centric versus HPC centric, but there are kind of other classes that is neither. But also, you have to consider about the cost, R&D, R&D costs and manufacturing or costs, where like it's not only the workflow is based on the latency requirement, is the what it takes to have the HPC quantum HPC systems in operating. What's the shortest path to get those systems up and running?
Absolutely. I think one of the metrics for success itself is one of the open questions that we are discussing, right? Is it everything from utilization to sort of latency to costs and so on, right? And what are all these metrics that we should be optimizing for, right? And one of the sort of standard conversation, I think even Armin might bring that up, is sometimes you are okay with maximizing utilization of the QPU, even if it means keeping your HPC idle, ready to sort of take the output in a sort of tight coupling, right? So at that point in time, it's not the utilization of the cumulative system, but maybe utilization of the more costlier QPU hardware itself that comes into picture. So all these trade-offs are something that we are hoping to document, right, as possibilities.
So okay, yeah, but you said that you have a preprint already posted, or you can give me a link. Yeah, I can give you feedback right away within a week. Yeah.
Sure. There is no preprint yet. It's I think this is a slide deck that we're working on, just a discussion right now. So there isn't like a paper out there yet.
Oh, I thought that there is a paper on architectures, like because we are working on something internally on that. But I thought that, we can sync on that. Okay, so because I think this is a very timely contribution. And I had a discussion with Amir on this. Because as we are trying to see how we can do quantum HPC integration, some of these kind of patterns that keep happening, and seeing like what are the general superclass of quantum algorithm. But once you go to quantum algorithm discovery, there are kind of other things. You can consider a hybrid with agentic AI and other things to discover algorithms and things that are more of a next generations systems. And So I just generally take home messages that people who talking about remote access and kind of tight integrations, not Nico, I think they're not having a long horizon in the, and I think once you have a system, it has to run all the type of jobs. Not, you can't just have a system that is running some algorithm, but it cannot do the others. So you need to have like a portability, and also be a system should respond to various users different days for different workloads. You cannot just change your architecture of a system every given day, given who log in to run a quantum algorithm. So I think my advice for tight integration is something that is robust and is going to stand the test of the time.
Great. Thanks a lot for the feedback. Yeah. Amar, did you want to go next?
I have a couple of quick questions. Again, so the dynamic circuit generation, is the target usage error correction, or are there different usages for dynamic circuit generation? That's one question. The second one is regarding circuit cutting. Are we expecting for circuit cutting that all the circuits are strictly independent and you can run them independently, or would there be some sort of relationship between the different parts of the circuit? I guess I'm not 100% clear on that.
Yeah, sure. So over here, this variant of dynamic circuit, right? So here, there's an inherent requirement of the application itself that you measure it and you change the circuit in order to get to a solution, right? So there's less from a optimization perspective and more from an inherent application characteristic, right? But that being said, your circuit cutting and knitting is more of an optimization that you use. Here again, you are generating dynamic circuits, except that these are split circuit sub-circuits over here. And in this particular case, these are independent sub-circuits that can run in parallel without any dependency. And the outputs of all these circuits are then combined together to get the final answer, right? So it's like, if you think of it from a DAG or a workflow perspective, loosely, you're splitting the DAG into different components, running those components independently, and then merging the results back together to get a final answer, right? Another one, when it comes from the ZNE and sort of some of the probabilistic noise correction, there you essentially do, for example, the quantum error correction circuits, right? So there you actually run these you decide circuits dynamically on the fly based on the user circuit, run them to get a sense of the noise profile of the various qubits, and then use that information to decide the layout of the user circuit itself, right? So there again, it's a dynamic circuit generation on the fly. You run it, profile it, and immediately you schedule so the user circuit, right? So these are different variants of where circuits themselves are dynamically either probed in the case of dynamic circuits and probed and sort of modified, or they are split, or you're sort of running profiling circuits ahead of time. So application focused, more scheduling, parallelism focused, as well as noise error correction focused. All three are valid scenarios for dynamic circuits.
Thank you. Go ahead, Ira.
Hi. So basically two questions or comments. One is on the parallelization, right? So beyond kind of the circuit cutting, where I think it's mostly driven by the limitations of a single computer where you partition the circuit into independent things. But more like on slide 8, right? I think are there other examples of things that are going to be parallelizable by the nature of the problem rather than by the limitations of the technology? And that seemed to be one of them. And maybe AFQMC is another example where each experiment is largely independent of the other, and then you kind of figure out which ones sort of stand. Are there any examples of parallelizable algorithms or workflows?
So far, the ones that we've come across are truly the QSVM and the QNN variants, where it's sort of there's a clear data parallelism that's present over here,
correct,
right?
Yeah.
But if you look at these dynamic circuits, these are again a form of sort of task parallelism, if you want to think of it in that way. Right?
Yeah.
So these are the two variants that we've seen sort of in practice, right? So there might be others, but we are hoping that we can find them through a collective measure, right? Yeah.
And a second quick question is, on the amount of data between kind of the classical world and the QPU world, right? To me, naively or at the moment, it's basically the description of the circuit, and then the output is the bit string with 1 or n shots depending on what is the task size, right? If you will, it's 1 shot versus many shots. Is there something more to it? Clearly this is my naive view. What do you see as sort of going forward, where sort of bigger pipelines are needed, or what would be there beyond these sort of in and out data sizes?
Right. So can you rephrase the statement? Was it in context of a particular application or yeah?
Yeah. Towards the end, you made a statement that you're looking at sort of how much bandwidth or what's required, the connectivity between the classical world and the QPU. If I look at the QPU, right? If you kind of include the compiler and the runtime of with the QPU device itself, it's the description of the circuit that was partitioned or not yet partitioned, broadly speaking. So that's relatively small in my opinion. Same thing like for the output of computation is when you stitch together, whether it's for the knitting purposes or for a stage, you get a bit string, and so and you get the probabilities or a histogram or per shot data. All of these seem to be fairly small. So to me, the fatness of the pie between the classical and the quantum is not interesting, in terms of today's, capabilities of networks and systems.
Right. I think so far, I don't know if it was the MCMC one or the SQD one. I think there was a comment that was made that I think maybe in the last meeting that we had on the Intel group, that at most it runs into gigabytes in size, right? So that might be marginally challenging if you're looking at far quantum, but still it's not so big that, and especially if you don't need tight coupling, right?
Yeah. Okay.
In such cases, even it's far quantum running into gigabytes, which is the most I think I've anecdotally been I've heard said, is not such a big deal. The question comes in if it is tight coupling, right? At that point in time, these start coming into play, right? So it has to be on the order of seconds or sub-second, right? Then even a few megabytes in a far quantum can be challenging.
Okay. Yeah, thanks. And I think it will evolve. And I was at the discussion last week at the work group, right? So indeed, but to me, the tighter you coupled, the less of a bandwidth requirement there is. If you imagine kind of the circuit and the output of the experiment, if you will, right, or task run. Cool. Thank you.
Right. Yeah. But at the same time, the more tighter the coupling, it also imposes restrictions on the type of hardware you can run it on, right? So the degrees of freedom reduce as well. So that's really the trade-off, right? So if you have a workflow with certain characteristics, right, what are the options that you have for scheduling it? If you have a choice of deployment models, right, or choice of data centers, where should you be running it, right? And on the flip side, to I think the earlier comment, right? So can I build a data center that can solve all problems, right? But at a manageable cost, right? So these are two extremes, right? So one solution, one integration solution that will solve all problems, but could be extremely costly. Or you have a choice of different data centers or integration models, and on the fly, depending on the application, you choose which one is appropriate for you, and you run it on that, right?
So I put a few links to some of the papers publicly, that are on archive, on the comments that I made earlier. Just want to mention something that when we are thinking about kind of distributed quantum computing, we need to think about the kind of distributions motivated at the problem space. Let's say when you just have like from the graph connectivity, then like saying like the sparse ones, wherever you have a sparse connectivity in the between the your logical variables, it might be a good place to cut, minimal number of zero, that kind of things. I would say this is in problem space. You could have a distributed quantum computing inspired from the algorithm space, based on the kind of subroutines, various things, is it iterative or not. I think it's kind of, I would go from this classification first. But then the third class is like less understood, is like you have distributed quantum computing based on the solution space, what the insights you get in the configuration space. And this is applicable in both classical and quantum. So when you're like, let's say you do sampling classical over a set of discrete variables, or it's actually in quantum domain, which is much more non-trivial. What kind of insight? And those are like really adaptable. You have to make decisions like on the runtime of the algorithm, and you need to preserve quantum coherence, and those are extremely tight integration. So it's kind of, but the first class, when it's like your insights in problem space, usually comes as a pre-processing. And once you start running, you don't need to have a tight integration. So I'm saying that this is a kind of a meta version of classifying some of this workflow under umbrella, especially when it comes to circuit synthesizing or dynamical circuit generation.
That's a good point. In fact, we try to incorporate some of these into the working document that we have, right? Or the working set of notes that we have, right? Because we do want to sort of try and come up with a classification model, and this might be a good starting point. Yeah.
Yeah. Okay. Yeah.
Yeah. So thanks to Hatim, I have the two missing slides, which I was just talking about, but didn't have the slides. It suddenly disappeared at the start of my presentation. So this is the sort of the device characterization circuit I was briefly talking about. So here again, what you're trying to do is based on the user's circuit that is provided, on the fly, you sort of end up constructing lightweight QIC circuits. That's a function of the user circuit. And you sort of execute that on the same quantum hardware to get a sense of the noise profile, and then use that to decide the layout for the user circuit, right? So you do the generate the QIC circuit, execute it, do an analysis of that, come up with a sort of real-time noise model, and then use that for the actual deployment of the user circuit. That's one. And the other one was the error mitigation one. And this again goes to Amir, your comment, right? So this is another example of a parallel execution of the circuit, but these are variants of the same circuit. And you want to run all of these variants and then do some kind of an aggregation or sort of some kind of a distribution over all of them to get the final answer. So these are all the original circuit with certain perturbations, as opposed to splitting a circuit or as opposed to doing a data parallel execution of the different circuits, right? So these are the three variants of the dynamic and parallel execution of the circuits that we've encountered.
So one thing to consider is that the kind of parallel quantum computing, when they're basically embarrassingly parallel. I think this was related to Amir's question earlier, versus things that are, you have to have non-trivial communication, and the communication could be one-way classical, two-way classical, or like actually quantum interconnect needed. So it's kind of different, and this could be applied for error mitigation and device characterization, as well as obviously error correction. When you have real-time decoding and things like that, you have these are examples of non-trivial, if you want to build distributed decoders and things like that, obviously you need interactions. But I would say some of the error mitigations are embarrassingly parallel. And you just can provide samples over identical, even circuits, and just collect statistics.
So I had a question about the tight integration model, or the as we move towards the fault tolerant. I guess that's not 100% clear to me, because what I've been hearing so far is with fault tolerant, your circuits are going to be deeper, they're going to take longer to execute. So I want to try to understand a little bit where the requirements would come up if you have like a fault tolerant circuit that you're executing, and what kind of interaction you will need with your HPC. So I don't know, like Masoud or Yogesh, if you guys have some ideas on that, or anybody else really, but just throw it out there.
Yeah, so this is a good question. So for some of the calculation, let's say electronic structure simulation, where the circuits are very deep in FTQC, runtimes could be days or weeks, could be months, like in principle, like it depends on the system. And so that would imply that in some of this, if you have the HPC and QC integration as like a more pre-processing or post-processing, you don't need a tight integration. But I think that's just more of, I would say, a naive implementation. There are scenarios that we are working that tight integration is needed even for those applications. But so sometimes, of course, in pre-filter and circuit depths would be much limited. Like let's say you go on 10 to 6 operation instead of 10 to 10 or 11. But whenever you have mid-circuit feed-forward operation at the logical layer, even within FDQC unit tight integration. So that's like a quick thing. So I mean, we can discuss this offline if you are interested more. So basically what I'm saying, mid-circuit feed-forward measurements need tight integration, period. And obviously that's kind of within the error correction cycles, but it could be outside of them as well.
But would you need HPC for that case? Like, do you need that feed forward or that data to be transferred, and do you need HPC there for right there for execution or for processing this feedback, or is just small classical close to the quantum sufficient?
Yeah, that's a good question. HPC, there are two things: HPC compute and HPC networking. You need HPC networking when you need those kind of short latency and high throughput at the application layer, as well as for real-time decoding. But the thing is that the compute, it depends how non-trivial is your pipeline. If you have to integrate this, like you are very far from embarrassing parallel, you collect information, you do conditional operations on generating secrets dynamically on the runtime, and you have to do AI, like let's say this is when you have AI HPC QC integration, then you need HPC because in some form, but of course, HPC is also, it depends. You are going for like a GPU based HPC. It means that a lot of you want to accelerate linear algebra operations that can be distributed and parallelized, but some or more conventional, like going to exascale machines. Those are it's a discussion that we can have, but in general, at least in the AI pipeline, you need some form of HPC. It might be in the kind of the time scales. Let's say if you have to make decisions on a massive number of degrees of freedom over a distributed system on the order of microseconds, you need to be able to compute very fast and communicate with short latency, and then you just need both HPC compute and networking. Yeah.
Thank you. Anybody else have questions, comments? Yogesh, do you have anything else to add?
No, I'm good. But this is an excellent discussion, and we have a lot of follow-on material for our next weekly meeting. So we'll try to sort of consolidate some of these thoughts, and sort of we can maybe discuss these in our next meeting. Thanks a lot, everyone. Yeah.
Thank you, everyone.